The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Self-driving cars are pretty cool, pretty hot nowadays, so we're going to use this as an example. And in the past, we have seen how we can give an autonomous vehicle a goal, some condition we want it to reach. For example, we might have a car that wants to pick up some passengers along the way, get to some destination, and maybe navigate some world. But let's consider that for something like a self-driving car, we also have a number of other goals or requirements that are sort of implicit along the way, in that we want our self-driving car to obey the rules of the road as it's driving. And these aren't just goal conditions, which is a sort of single goal that you're trying to reach, but these are sort of goals that you're trying to maintain throughout the path that you're traveling. So one example of this is a traffic light. So maybe you guys can help me out with this. Just in plain English, how would you describe the rules of how you would want a car to behave when it comes across a traffic light? Anything very simple. Yep.
Slow down if you see yellow, stop if you see red, go if you see green.
Yep. Yeah. So pretty much stop if you see red, go if you see green, and specifically if you see red and you stop, you're going to want to stop until you see the green, at which point that sort of condition that you're stopping goes away and you're able to move on. And then in addition to things like obeying traffic lights, there might also be some other rules of the road that we want to follow. For example, we might want to always stay within the speed limit. And then there might also be some other practical conditions of driving on the road, which is that at some point we're going to need to refuel. And if we consider a car that might be driving for a really long time, one logical statement we could say about the path that this car takes and the sequence of states that it goes through is that at every point in time, we want the plan to have some future state when we are going to visit a gas station. So this isn't just like a single goal that we're trying to reach, but over a very long time, even if we consider that this car can drive an infinite amount of time, at every point in the time, we're going to need to be thinking ahead that there's going to be some time when we reach a gas station and refuel. So these types of conditions, things like staying at a red light until it turns green, always staying within a certain speed limit, or always having some path in the future, some state in the future when we reach a gas station, are things that we can express with a type of logic called temporal logic. And there are two things that we hope you're going to be able to do by the time you leave this lecture. The first is to be able to model these temporally extended goals using a specific type of temporal logic called linear temporal logic, or LTL. And secondly, we're going to hope that you'll be able to actually apply this to planning, create plans with these temporally extended goals, and in addition to just sort of this regular planning we've been dealing with, actually incorporating this idea of preferences into your plans. So a preference basically is not a required condition, but a desired condition that you can use to select between alternative paths. So you might have many different ways that you could reach your goal, but we can use some of these temporally extended goals, like maybe you prefer to break as few of the rules of the road as you can, and you can use those as preferences to choose between plans. So just as an outline, first we're just going to do a little introduction to linear temporal logic. We're going to talk about what this is, what LTL is, why you want to use it. And we're going to go through the syntax and the semantics of different LTL operators. Then we're going to walk you through some example LTL problems and actually talk about its applications to planning, how you create plans with these linear temporal logic and temporal goals. Finally, we're going to incorporate preferences into this, talk about how you express preferences, and specifically talk about a language called LPP that allows you to plan with temporal logic and preferences. So now for the sort of introduction to linear temporal logic. Temporal logic at its core is a formalism for specifying properties of a system that vary with time. So these aren't just conditions that are true at a single state, which is what we've mostly been dealing with prepositional logic, right? So we've been saying things like, condition A and B, but not C, are true at a given state, and that's prepositional logic. Temporal logic is sort of a layer on top of that when we're dealing not just with what's true at a single state, but actually extending that over time as the system moves through a sequence of states and expressing properties on a temporal level. So you might have a system that can be represented as a state machine, an automata, and it can go through a sequence of different states. And while you might be able to represent the whole system like this, if we actually execute the system, we're going to get one path through the system. And we call that's often called a trace of the system. You can also think of it as a timeline of the system. So one example timeline of this system is, it might start in state A, then go to state C, and then go to D, and keep looping around in D forever. So that's one trace or one timeline of the system. And that's really just a sequence of states that it goes through. And in the past, we've seen these in some of the problem sets. For example, when we were modeling the warp reactor, we've had the valves that could transition between open and closed states. It could also be the whole system of a starship going through different planets, transitioning through a larger set of locations, picking up passengers, dropping them off. So these could be quite complex. And so as I said, previously in our problems that we've been modeling, we've been going through a system and we've been searching for a single state that satisfies all of our goal conditions. Right, like maybe we want to reach Lavinia and save a certain number of people. But with temporal logic, we can actually express goals that are satisfied over a number of states. And this allows us to do some more expressive goals than we could capture just by looking at a single state at the end. So for example, what if a problem requires some condition to be met until another condition is met? And for example, when you see a red light, that implies that we should stop until we see a green light. And if we look at a timeline or a trace of one of these systems, that might look something like this. So we're going along through our system, and at one of the states we see the red light, so that adds this condition that we should stop. And then that condition will hold forever until we see a green light, at which point that condition is dropped and we can keep moving on. Another example where we might want to use temporal logic is, what if our problem requires a condition to always eventually be met? And this is what I was talking about with the gas station. So we might be going on forever, and there should always be some point in the future when we do have a state where we're at a gas station. So we might start our system at a certain state, and our plan says that at some point we do reach a gas station. So that's good. But then when we get to the next state, we also want it to be true that from that point on, we're going to reach another gas station. And after that, going on and on and on into the future. These are things that you can't express very easily with the types of logic that we've been dealing with before. So one important distinction that we should clear up before we really dive into the syntax of how these linear temporal logics work is the difference between branching time and linear time. There are really two different models of time that we can be working with. There's two different types of temporal logic that exist to express these different types of time. So linear time is more similar to the world that we live in. Unless you're living in some sci-fi movie where time is branching into different realities and all sorts of crazy stuff is going on, you can think of time as just this linear timeline. So right now, there's one future state that's going to happen for me, and regardless of how many options I have, there's one realization of the time. And what this lets us do is that it gives us a single path for our system, and we can reason very exactly about the conditions that are met within that path. And this lets us use the lets us describe what will always happen in the system. For example, we can guarantee that we always stop at a red light until we see a green light, or we always stay within the speed limit. This is contrasted with a different model of time called branching time. And in this model of time, at each time instant, we consider all possible futures. So if we have multiple actions that we could perform at a given state, we're going to consider different timelines that branch off from each of those possible behaviors. And this results in alternate courses of time that we can reason about as a set. And instead of thinking about this as always conditions, so our path always does this, we can think about this more as possibilities. If we're using branching time, we can say, at this state in time, there exists a future path in which we will always stay under the speed limit. Or at this point in time, all of our future paths satisfy a certain condition. So, whereas linear temporal logic is more about guaranteeing what will happen on a given path, branching time allows us to reason about what might possibly happen in a system. So for our purposes with planning, in part because it's more tractable, and in part because it gives us an exact analysis of a given path, we're going to be dealing with linear time, and for that reason we use what's called linear temporal logic. There's a different type of temporal logic. There's one called CTL and CTL star that deal with branching time. And what those are sort of an extension of linear temporal logic that add a few other operators that allow you to reason over multiple paths. But for our purposes, we're just going to be using the linear time model. So kind of as a recap of what linear temporal logic involves, we're using this linear time model. Another important distinction is that we're actually going to be talking about infinite sequences of states. So instead of us just reasoning up until a certain goal condition is met, we're thinking about systems that could theoretically keep transitioning over time, over and over and over into the future. So if you have one of these state machines, you can think at each time step it's going to visit a new state. And if you give it enough time, it's just going to generate an infinite sequence of states. And we can actually express properties that can hold over an infinite number of states, not just the discrete number of states that we might usually think of to reach a goal. And linear temporal logic can actually be modified to work with discrete set of states. It just requires an additional operator. But the ability to reason about infinite sequences of states gives us a lot of power in talking about guarantees for our system, regardless of how much time we're talking about. Finally, all the operators we're going to be looking at in our logic system are what we call forward-looking conditions. So this is, when we're given a state, we're going to be reasoning about what's going to happen in the future for potentially infinite amount of time in the future. There's sort of a symmetric version of this logic that reasons about the past. So for example, we could say, talk about guarantees that something will eventually happen in the future. There's a sort of a symmetric version where we could talk about, given a certain state, we can guarantee that something had eventually happened in the past. But for us, and that we're going to focus on planning, we're typically planning about what to do in the future, it makes more sense for us to use this future-looking set of operators. And so I guess one little nuance here that I sort of pointed out in the previous slide is that because we're using a linear model of time and not a branching model of time, we're going to be expressing properties that happen over a single path of states and not properties that happen over a separate path of states. So finally, I'm just going to talk about a couple of the main applications for linear temporal logic before Ellie will dive in and actually talk more about the semantics and the syntax of how we use this logic. So the first main use is verification and model checking. We can use this linear temporal logic to create guarantees about a system and formally verify it for a couple different properties. For example, we can talk about the safety of the system. We can say, Over the course of this system, we guarantee that it will never enter a state with a certain condition. We could also talk about the maintenance of properties. So over the entire lifetime of this system, we guarantee that a certain condition will always hold. The other main application for temporal logic, the one that we're going to be focusing on, is for planning. And this is planning using these temporally extended goals that I've been talking about. And it actually extends nicely to talking about temporally extended preferences. So this is, given that we have a number of different paths that could reach a goal, we can actually look at all of those and see which paths satisfy certain conditions over the sequence of states, and use those conditions as a way of choosing which ones we prefer. So with that, Ellie is now going to talk about some of the syntax of linear temporal logic.
Hi guys, my name is Ellie, and I'm going to be talking about the syntax of LTL. So, an LTL formula is a series of states, and at each state you can have various propositions that can be either true or false. So, for example, is it okay if I erase this?
Yeah, go ahead.
So for example, we can have, as Ben's animation showed, we have a series of states that goes on to infinity, and at each state we can have propositions that are either true or false. So the traffic light could be red, could be an example of a proposition. We could be stopped, etc. And there's various logical operators that we can apply to these formulas, these sets of states, and we can determine if these logical operators are either true or false about each set of states, each formula. So there's the not operator, the or operator, the and, the implies, if and only if, and like I said, the state, each proposition at the state can either be true or false. So just to go into some examples of these, the logical operator true says that there is, essentially what the operator true says is it's not saying, oh, this state is true. The operator just true says that there are states for all infinity. So true is always true. So no matter what you had for your states here, the logical operator true holds. However, when you talk about the logical operator true with respect to a certain state or a certain proposition, then it can either be true or false. So for example here, the logical operator red, light, is true at the first state. If this was green, then the logical operator red would be false at the first state. Does that make sense? Alright. One important thing to note about the logical operators is that they just apply to the very first state in your sequence. So when we're discussing logical operators, we haven't gotten to the point where we can express temporal information about our sequence of states. The next operator is not. So as you can see here, the traffic light is red at the first state. So the traffic light not green holds because the proposition green is not true at the first state. And the logical operator and, right at this first state is we're at the red light and we're getting gas. And so both that we're at the red light and that we're getting gas holds for the first state. And then the operator or essentially says, I guess a lot of this is probably removed to you guys, logical operators, but essentially if you have red or green, then you could either have the traffic light be red or the traffic light be green at the first state. And as long as one of those two holds or both of them holds, then it's true. And one thing to note about or, implies, and if and only if, these can be rewritten with just the logical operators and not. So another way of expressing red and green is to say that you can't have a scenario where both it's not red and it's not green. And I'm not going to go over that for implies and if and only if, just for the sake of time. So that's just a review of the logical operators, and now we're going to go into the temporal operators. So when we're talking about our autonomous car, what are some useful temporal operators? Because up until now, we just are describing the first state in our sequence, which isn't really useful if we want to talk about the entire set of sequences, or set of states. So what do you guys think are some useful things that we want to be able to describe? I know Ben touched on some of them at the beginning, but if you guys could recount some of them. Yes?
State transition.
Mm-hmm. State transitions. So, exactly. So if I'm in a state right now, might I be concerned about the next state? Is that kind of like what you're saying? Exactly, yeah. So next is one of the things that we might be concerned about. The next state. Are there any other things you guys can think of? Yes?
Always or global?
Yeah, exactly. Always. So like Ben said, we always want to follow the speed limit. We always want to be under 35 miles an hour, whatever the speed limit is. Anything else? Yes? Until? Yep. So, like he said, we want to be stopped until the light turns green. Yes?
Eventually.
Eventually, yep. So we eventually want to get gas. And next, eventually, any other things? Yes?
At this stage.
At this state, yep. And so at this state is kind of what the logical operators were doing at the beginning, but I agree that's something we have to be able to express. So that's not a specific temporal operator, but it's included in the logical one, so I'll just write it up here for you.
Can I ask a question?
Uh-huh.
So the logical operators are they acting on so they're acting per state, they're not acting on the entire chain. These are
Exactly,
acting-
they act per state. And so if you just wrote the logical operators by the definition of LTO, it means let's just analyze the first state and see if it's true. And so it won't tell us anything about the third state or the fourth state or the second state, which is why we have to look at like the next state. So yeah. Any other questions? Okay. So, like you said, next is an important one. So, right here we consider, okay, the next light will be green. And until is the one that she mentioned. So the light will be red until it becomes green. Eventually. So the light will eventually, at some point in the future, turn green. So we might be waiting here at the red light for a long time, but eventually it's going to turn green for us. The light will always be red. So I guess you're stuck at the traffic light for a long time. Or globally, that's another name for always. And lastly, this one is a little bit less intuitive. So what this is saying is the light will always be red until another circumstance coincides at the same state. So the light will be always red until the car gets gas, and then after it gets its gas, then the red is released, and the light can be either green or red after that. So we have red, 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 until we have both red and gas. And then it can be green or it can be red after that, and it's not constrained to being red. Does that make sense? That was a little bit less intuitive, so. Is that good? Okay. Alright, so now that we've gone over just the intuitive understanding of that, I'm going to give you the actual syntax for that. So, X is representative of next. So in the first state, we don't care if P is true. P could be not true, P could be true, it doesn't matter. But in the second state, the next one after the first state, P has to hold in order for XP to be a true statement about our sequence of states. So, what do you guys think? If I wrote this, what would that mean? Yep. So this one over here?
Sure, whatever.
Yeah, perfect. The until operator essentially says, like Ben said, we're stopped until the light is green. So if you have P until W, you just P has to be true at every state until W, and after that point P can be whatever it wants to be. The eventually or future operator says that at some point in the future we will get gas. However, it's important to note, I know when we talked about getting gas, we said, oh, we have to always get gas at some point in the future, but the future eventually operator is just at one point in the future. So once you get gas, you don't have to get it again. Yes?
On the previous slide, you had a note at the bottom that said that W is required to become true. Does that mean an until operator also implies a future operator on the W?
Yeah. Yep. But it's just the added condition that P will be true until the W.
But like whenever you use until, you say P until W.
Yeah.
You also have to add like at some point in the future W.
Yeah. Yep, you're right. Alright.
But I mean, it'd be possible your system just stays P, right?
It could, yeah. But then if your system, that'd be totally fine if you had your system just be P, but then the operator P until W wouldn't hold unless you had a W at some point in that sequence of P's. Does that make sense? Here.
I mean, I guess it does if that's the way to do it, but it doesn't make sense not to do it.
So you're saying that we can have a bunch of P's, right? At every state? And I'm saying that this is a fine state to have. You can have whatever you want as your state, and we're just analyzing if a sentence is true about it. So this statement, it's not true, or sorry, I'm saying that it's not true that we have P until W because there's no W in our state. But if we add in W somewhere, and we keep all the P's, then it's true because it has P up until we get to a W. Does that make sense?
I mean, it makes sense if that's the rule, but
Yeah.
it doesn't make sense to me why.
Okay.
Because the statement is true even if W never appears. You have P until W, which never happened.
Yeah, if W never happened, then it wouldn't be true.
I mean, it would be technically English language, it would be true. I mean, I guess it's not.
If you have P out to infinity and you never have W, P until W is true.
P until anything is true.
Yeah.
Like if you say that I'm hungry until I eat and you never eat, then you will always be hungry.
Yeah.
Oh, I see. Yeah. So that makes sense in logical sense, but that's not how it's described in
Yeah.
LTL.
There's also an operator that's sort of like unofficial called the weak until, and that's sort of saying like P until W or always P. So that kind of like gets rid of the condition that it reaches W at some point.
It aligns more with the English.
Yeah.
Yeah.
But just the until operator on its own is sort of like a strong until.
Yeah.
So that adds the.
Yeah, that's fine.
Okay.
This is the way it works.
Yeah. Sometimes, I get confused about the syntax. I feel like why they necessarily chose certain things. But okay. And then the globally one, which we said this is the one that you're just describing exactly. We have to have P at every single state in the future. And then the release operator is you have to have P until you have W, but P and W also have to share the same state when they switch from. So it's in until we don't have to have the P here, but with release you have to have the P and W occur at the same state. Does that make sense? Yes. Okay. So just like the OR operator can be described using not and, the future, release, and globally operators can also be described using other temporal operators. And so, just as an exercise, can any of you guys tell me which, these are not in order, which of these line up with the other, like whichever ones they line up with? And I'll give you guys like 3 minutes to just think about it, and then we'll work through it together on the board. And if you guys come up with it in less than 2 minutes, feel free to shut up what you think. Alright, so have any of you guys thought about which ones might relate to which ones? Does anyone have any suggestions?
The
Yeah?
first one's the top one.
This one is the top one. That's exactly right. So, let's consider the state again. So, true, the statement true says, it doesn't say anything about what the propositions are. It's just something that's true for all states, right? So if we're saying true until P, that means that you can have whatever you want until P occurs. So does that make sense that at some point in the future P has to occur? Exactly because we had the strong until, right? Does that make sense to everyone? Yes, I see some headphones. Cool. Alright, and now what about this one? We have not F, not P. So this is saying that at some point, it is the case that at some point in the future you don't have P. So what do you think that would correspond to? If at some point in the future you can't have this situation where there's not P.
The third one.
The third one? Globally, right? So if you have P at every single state, then you never have the situation where you don't have P, right? And so that leaves this last one. We have, you don't have a scenario where you have not P until not W. So, if you have not, okay, this one's a little harder to explain. But I'll come back to that one at the end, okay? But it's just important to remember that you can describe these operators with simpler terms so that your planner doesn't have to deal with the global operator, the release operator, the eventually operator. It can have less tools to deal with. So, yeah, you guys are right. Perfect. And then this is just a recap of the different operators and the other ways that you can express them. And so, there's two more really cool things that you can do combining these different operators. And the first is that, remember when Ben was describing that we need to get gas, and we need to get it in the future, but even after we get gas, we're going to have to get it again sometime in the future? So it's important that we can describe something that happens infinitely often. And the way that we describe that is saying that we always have the scenario where you will eventually reach P. So, I didn't think of another way to describe that, but does that make sense that like, right now in the future, I'm going to get gas. And even after I get that gas, I will eventually in the future also need to get gas again, because your car will always be needing to get gas. Does that make sense? Cool. And then eventually, forever, is another scenario that's important to describe. So, let's say that the traffic light will eventually turn green forever. We need to be able to say that at some point in the future, although we don't know when, the traffic light will turn green. So, the future operator says that at some point in the future, we will have something come true. And so at this state, P becomes true, but the global operator says that happens from this state forever afterwards, which is saying that you eventually will always have the state P be true. Do you guys have any questions on that? Did I explain that to you? Okay.
It seems weird to me that the gas thing is becoming this like occasional temporal operator instead of just like the state that we actually have gas would just be a logical thing that.
Oh yeah.
I mean, why is the act of getting gas showing up here like that versus just we always need some quantity of gas?
That's true. We do always need some quantity of gas, and you would describe it, like you said, just with the always operator. But I guess my action of getting gas is I was thinking of actually driving up to the gas station and and filling it up with gas. And if you didn't do that, you wouldn't be able to like always have gas. Does that make sense?
Right. So like I would think that always have gas would make that fall plan and have to get gas.
Yeah, and depending on how you make your model, that you definitely could do that, and that definitely would satisfy the condition.
But this is the usual way to deal with it?
Well, it depends on the situation. Maybe maybe you instead want to say at some point in the future the light will always be green because you want to ensure that cars can go through, and even if it turns red, at some point it will be green in the future. So it really depends on your model and how. I think the way you're saying it, where you always want to have gas, and the proposition gas is how much gas you have in your tank, and if you have it or don't, then I think that would be a really good way to model it too.
I mean, if you said I have to get gas, I plan it for next week, and I run out of gas next week. You know what I mean? Like, you have to somehow be tracking the quantity of gas also.
Yeah, I agree. I was just using it as an example to explain the concept, but I agree that definitely probably would be a better way to model it.
I think in both cases what it could represent is having gas all the time, or explicitly saying that you're going to be in a gas station eventually, always eventually. That depends on how, maybe you're going to always have a gas from a station as opposed to getting a gas from elsewhere. So that depends on what you want to model, but I think both will work.
So infinite often, it doesn't really care about how frequent it is.
No, yeah, it doesn't care how frequently.
But what about this situation? For instance, something happens every 60 years. My system lifetime circle is 30 years. So which means something happened only once. So in this case, infinite often and happen in future. The future operator could be the same, right?
Can you repeat that again?
So for instance, something happens every 60 years. My system life cycle is 30 years. After 30 years, I have to get rid of the system. Okay. And then, so during this period of time, maybe only one thing happens. Also, it happens often, infinitely, but in the life cycle of the system only happens once. And therefore, in this condition, the infinite often it should be exactly the same as the future, right? At the current state, something happened in the future of the system and it never happened again.
Kind of. So when you're talking about a system that's dying after 30 years, the LTO doesn't actually model something that ends. It models something for infinity, although there is an extension to LTO that can incorporate that into it, having it have an actual end goal state. And I think in that case, then infinitely often would be different and would I don't know exactly how that would apply in that situation. Do you know, Ben? I know you would kind of.
Well, there's something called metric temporal logic, which associates like a time scale with each of these operators. So I think you'd have to use that if you were trying to express that you had to always meet this condition still within your lifetime. You could have some sort of qualifier to these operators that specified actually in time where that operator had future.
So which means if I only use this infinite often, so probably this scenario is something happen a little bit more frequent, during the system lifetime, right? Not like something, happen every 100 years or 200 years.
Yeah, it's important that LTO is only dealing, or the LTO we're explaining here is only dealing with infinite states. Mm-hmm. And so I agree, it's a little bit, you have to think about that process of how do you apply something that goes on forever to a real system that obviously doesn't go on forever.
Well, there has to be a way to, the future thing, like if he has a system that lasts 30 years and you say future P, somewhere in your design of the system is going to say that the constraint on future P is that it has to happen within 30 years, right? Because like future P here for getting gas has to happen before I run out of gas. It's not just, this representation says it just happens in the future, but somewhere in your constraint checking, it's going to say, hey, we didn't get gas in this plant soon enough, right?
Yeah.
Somehow.
Yeah, that's definitely true. And these are just tools to help you model it, but it's definitely not the entire model of your system, obviously. And so I agree that you definitely would have to incorporate that in. And for finite systems, you'll have to account for that. And that's why they have the extension of LTO to finite systems. Which we can certainly send out a link of the paper and where we got the information to the class if you guys would like that. Huh?
Yeah, I think you guys have done a very good job of answering the questions. The three extensions to LTO that I found to be the most relevant, the kinds of things that we're doing is metric temporal logic, which is the first one that you mentioned. Also to be able to have it over bounded time, which is related, you mentioned. And then the last one is to deal with uncertainty, is then a probabilistic linear temporal logic.
Okay, cool. Right. So I meant to have this as 2 separate slides, but what are some true statements about this LTO that you guys can tell you about to look at this, or do, and explain why if you look at it? Okay, so why is the next red true?
Next step is still red.
Yep, exactly, because the next one is red. Why is it true that in the future there's green? Yep, yeah, because in the future there's green. And why is it true that there's red until green? Exactly. So it makes sense that if all of these are true, that this culmination of the and statements between all of them is also true, right? And so you could do that with or as well, or you could do that with, if you had sequences behind here, you could put a future around this whole thing, and it would be true that at some point in the future, all of this would hold. Does that make sense? Yes? Okay.
Well, even right there is true, right? Is the next step.
Yep, exactly. I was just saying if you had more things in the past and you were considering from some previous. Alright, so now Navi's going to talk about expressing LTL in PDDL3.
So Ben and Ellie has guided you through how expressive LTL formulation is. I'm going to formulate the LTL in a classical planner like PDDL. Now I'm using PDDL3, which is an extension, proposed extension of PDDL 2.2, which supports some of the LTL operators. So these are the basic operators that you can use to express the constraints and goals of your plan. So you have at A, always, sometimes, within, at most once, sometime after, sometime before, always within, and holding during. So the num here is the numeric literals that you can specify. And these are the ellipses represents already existing goal description predicates. So some of the operators may look familiar to you because they can also be used to express the constraint in STN, the simple temporal network that we learned in class. And there are some operators that are unique to the LTL or other kinds like matrix, temporal network, like always, for example. So now we are going to take a look at how you can express the operators using the PDL3 language. So next we can use within one occurrence to model next because there is no explicit next in the PDL3, and you can use always until to express until. And in the future, you use sometimes after, and globally, you can use always. And for the least, since it can always be omega or always until omega when you see p, you can use all plus to model this least. Okay, let's see some example. So if your goal is to have the traffic light turn red in the next state, you would want to formulate it using within one occurrence, the traffic light will turn red. And let's take a look at a more complicated example. So if you want to model a goal saying that the traffic light will turn red, it will be green until it turns red. At which point it will be red forever. So this is a temporal logic predicates that express this goal, and then. If you want to model that using PDDL, there's a direct mapping. You can see the direct mapping between the predicates and the PDDL. So this is basically saying if it will always be green until it turns red, and turning red implies that it will always turn red. So next, Melise will tell us how to map between the LTL to PDDL via Gucci automata, which is specialized automata.
Cool. So I'm Marlies. I'm gonna kind of bridge the gap between LTL and the planning world. So this is kind of a framework for how you would go from taking a problem with temporally extended goals all the way to a plan. So as you can kind of imagine from what Ben and Ellie were talking about, LTL is pretty expressive. You can express a lot of different types of goals that include more temporal properties than just a time window for a goal to be completed. So once you have kind of a defined problem with these temporally extended goals, then you want to model it in a language like LTL or PDDL. So if you have a language like PDDL and you have a planner that can do an algorithm called progression, which I'll talk about a little later, you can go directly to plan. Basically how progression works is it's kind of an algorithm that tells you when you're analyzing a state and you're analyzing LTL-like formulas that are true in a specific state, how to push formulas that you need to evaluate later on to the next state, and how to keep track of things that you need to continue to evaluate for satisfaction in future states. Another way you can do this is by taking LTL formulations and translating them into Bushi automata. So Bushi automata are basically finite state machines that are extended to handle infinite sequence of states. And I'll get into more about how Bushi automata work. After you have a Bushi automata, you can then translate that into PDDL2, which you guys are all familiar with. And then that PDDL2, you can just run with the classical planner and get a plan. So a little bit more about Bushi automata. Again, like I said, it's an extension of a finite state machine. Oh, yes, sir.
Why would you say on Bushi automata if you can just use a planner that'll go from PDDL3 straight to the plan?
I guess it just depends on how, what kind of planners you have access to, what systems you have. It's done both ways. So PDDL3 is still kind of new, so there's not a lot of planners that actually have progression and can handle PDDL3.
It's also the case that the particular algorithms, right, that are trying to either do verification or planning, maybe exploiting particular properties of the Bushi automaton, as opposed to the properties of the native language.
So you guys are all familiar with regular state machines. Bushi automata has a very similar formulation with some slight differences. You have a set of states, you have an initial state, you have a transition relation, and then you have a set of accepting states. These accepting states are essentially what replaces finite states in a state machine. You also have a set of symbols that are basically the transitions between states. So what an accepting state is a Bushi automata can only be valid if the sequence of transitions visits an accepting state an infinite amount of times. So I'll get into a couple examples. So let's say you want to model ticking, talking of a clock. This is just a regular finite state machine. As you can see, after some number of ticks and talks, you get into S2, and you're in S2 because the transition is only a self-loop. So you're in S2 basically forever once you get to S2. So we can model this as a Bushi automata by making S2 an accepting state. This example, making it a Bushi automata doesn't really do anything for you. It's just kind of to illustrate what the accepting state does. So the accepting words are a sequence of transitions. In this case would be, there's infinite combinations of ticks and talks that would make this Bushi automata valid. Does that make sense? Questions about that? Here's another example. For example, if I changed what my accepting state was. So if my accepting state was S1, I now have to visit S1 an infinite amount of times for this Bushi automata to be valid. That means the only valid sequence of transitions I could have is talk, tick, 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 tick for an infinite amount of times. So you can kind of represent different things and different sequences of inputs you might want to have based on which accepting state you use. This is another example. If you wanted your clock to be tick tock, tick tock, tick tock, you can have more than one accepting state, and now I have to visit S0 and S1 an infinite amount of times if I want this Bushi automata to be valid. So then the sequence of transitions I get is tick tock, tick tock, tick tock. Does anyone have any questions generally about like general Bushi automata? Okay. I might have to see how we model LTL as Bushi automata. So here's an example of one of these LTL formula modeled as Bushi automata. You guys take a few minutes and see if you can get which one this one might be. just so that everyone can kind of see that. In future, eventually, remember, that means that eventually P has to be true at least once. So from any sort of kind of input state, you go into S0, and then I could have not P for some amount of time, but as soon as I have P, I have to get to P because I have to be in my accepting state an infinite amount of times. So I have to execute P at some point to get to my accepting state for this Bushi automata to be valid. And then once I'm in S1, I can have any other amount of inputs. I'll always be in S1, and that's what the true label means.
And it's also something stronger, right? Which is it's eventually globally.
Right.
Right.
Yeah. So actually, in this case, after I get here, my input could be anything. So this basically just says that from my initial state, I have to execute P at least once to get to this accepting state. And once I'm there, I can be there. I'm always there. Any input will leave me in S1.
So just to make this clear for myself and maybe for others, the thing that's being executed or that's at like R state is the thing that's on the loop. So like if you go from S0 to S0, that's essentially saying that like one of the nodes is not P. If you go from S0 to S1, it's saying that one of the nodes is P.
Yeah.
Right?
Yeah.
And you go from S1 to S1 and saying whatever it can be because you just have the true.
Yeah.
Okay.
So if you put P where the true is right now, then you will have the global.
Yeah.
Right, that's what I missed. By the way, you guys have 25 more minutes.
Okay. So you guys are exactly right. This is future. So an accepted sequence of propositions would be not P, then you hit P, then it could be anything after you get to P. And in this case, for Bushi automata states, which are kind of like Ellie pointed out, are slightly different than the LTL states we've been talking about. In this case, you're in S0, and then once you get to S1, you're forever in S1. So globally it looks pretty similar to this. Can anyone take a few minutes to think about how I might change this Bushi automata to fulfill globally operator?
Single accepting state of the loop of P.
Yeah, exactly. That's exactly what I said. So you have initially your first state that you're in, because P has to be true forever after you get to this first state. You have an accepting state P. You can also model not P if you want to. You can also just have this single state, which would encapsulate exactly what globally is. So this is kind of how to go from LTL to Bushi automata. In kind of a real-world scenario where you have multiple LTL formulas, kind of all combined, your Bushi automata are going to look a little bit more complicated than this. You can have multiple accepting states, like I said, but it's kind of a cool way to model what an LTL is trying to represent. So this is, yes, sorry.
Right. When you have the not P transition out of there, like it's possible you could come into S0, you would accept the Bushi automata, but then you would go to S1, right?
So, accepting a Bushi automata is a little confusing. A Bushi automata is only valid if the infinite sequence of states satisfies it. So, if I were to go to P and not P, and my sequence of transitions was P, 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 not P, then that would not be a valid sequence of transitions for this Bushi automata, because I'm transitioning out of my accepting state, which I need to have been in for an infinite amount of times, and there's no way I can get back to this accepting state. So there's also a more defined algorithm. That was kind of just like an intuitive way to build a Bushi automata. There's an algorithm. The one that's most popularly used was developed by Girth. This is kind of a pseudocode version of the algorithm. You go from LTL to Bushi. As you notice, it actually uses progression, which is something that planners that take PDDL use to generate plans. An important thing to note, which I won't go into too much detail, this algorithm generates a generalized Bushi automata, which you then need to change to a simple Bushi automata. The difference is a generalized Bushi automata has a set of sets of accepting states. So for a generalized Bushi automata to be accepted, you need to visit an accepting state in each one of those sets of accepting states. At least one of those states has to be visited. For a simple Bushi automata, you only have one set of accepting states, and you can visit any one of those states for the Boucher automata to be valid. The translation between those two is a little bit more complicated, and we'll have papers in our reference that will walk through how to do that, but we're not going to do that now. This is the progression algorithm. Basically, it just tells you how if you have a LTO formula F and some current state N, and some, usually they involve some time step because we're in the real world and we can't really model infinite amount of time and we have to kind of make it discrete. So if you have some time step between successive states, how do you push certain LTO formulas onto next states to be evaluated later? For example, I'll take this next F as an example. So if F was the next F of some LTO formula, you would need to append that formula to the next state to be evaluated in the next state to see if that's going to be true or not. Similar things for until and I won't go through this formally, but it's here for reference. So the next step to this process is going from Boucher automata to PDDL2. This process is kind of confusing, at least it's confusing for me to understand. So the first thing I'll say is that Boucher states are not equivalent to traditional PDDL states. In a PDDL state, if you have two states that have the same number of the same propositions that are true and false, those states are identical. In a Boucher automata, that's not necessarily true. In a Boucher automata, you also have to encapsulate which transitions you can make out of each state. So S1 and S2 could have the same set of propositions that are true that hold, but out of S1, I should back up. This is the Boucher automata for future globally, which is what Professor Williams was talking about. So if I enter in S1, the star means I can have any sort of transition I want in S1, and then at some point I make the transition P, and when I'm in S2, I'm in P for, I have to take the transition P forever. However, if I get a sequence of inputs, let's say I get P and then B, and then P again, and then P again, it's not clear if I'm in S1 or S2, because in S1 I can execute any kind of state I want, and in S1 I can execute any transition I want, and S2 I have to execute only P. So if I got a sequence of P's, I could be in either state. So you need something else to add to PDDL2 to basically determine which state you're in and which transitions you can make from that state. Does that kind of make some sense? Okay, so there's two ways you can kind of transform PDDL2 to kind of encapsulate what Boucher automata encapsulates. The first thing is you can create new actions that encapsulate the allowable transitions in each state. This would basically mean that for every action you have in your traditional PDDL, you have to create an action for, basically a repetitive action for each one of these states, so you know exactly which transition you can take out of that state. This could get long, because you have to make a new action for every single one of these states for every action that you want to take. But that is one way you can do it. Another way you can do it is introducing derived predicates. Derived predicates are predicates that don't depend on the actions at all and just depend on some other formula in your plan. So, for example, we could have a derived predicate that explicitly tells you whether you're in S1 or whether you're in S2. And you can use these predicates in your actions in PDDL2 to make sure you know which state S1 or S2 you're in your Boucher automata. And then, in your formulation of your plan, you set your final state to be one of the accepting states. So I guess that kind of answers one of the questions about how you go from infinite to finite. The accepting state is usually what you place as your final state.
And then the derived predicates appear purely in the preconditions, or do they also appear in the effects?
They also appear in the effects, because you need to know if you have transitioned out of S1 to S2. So you likely have a derived predicate for both S1 and a derived predicate for S2. And that is also kind of a lot of work to add to a PDDL2 problem, but it's definitely shorter than the first way. And it definitely encapsulates everything that a Boucher automata encapsulates. Does anyone have any questions about that?
So you're changing the action then?
Yeah, so you're changing the action, but you don't need to make a new action for every state. In the first formulation, let's say I have some traditional action, like move block or something. I have to create a move block action for each one of these states because I need to know exactly which transitions I can take out of that action.
And the second example?
And then the second one, I can just have one move block, But in my move block, I'll have a derived predicate that tells me which state I'm in when I execute that action. So the number of actions you have to write is less because you explicitly have predicates that are telling you which state that you're in at each time. Now I'm going to hand it over to, if there are no more questions, hand it over to Mark, who's going to talk about preferences.
All right, so I'm getting a little low on time, but that's okay. So now I'll transition to talking about, we've talked about temporally extended goals, and we've said that goals are things that always have to be true in the plan. So now let's talk about preferences. Preferences are things that don't necessarily have to be true, but things that you'd like to be true. So in the classical planning problem, we can formulate it like that. We have a set of states S, initial state S0, a set of operators, and a set of goal states. And the problem is to transition from your initial state to any state that fulfills your goal state using the operators in A. In a preference-based planning problem, we introduce this additional field R, which is a partial or total relation expressing preferences between plans. And this is a little preference symbol right there. So that basically tells you if there are multiple plans to accomplish your goal, which one do you want to use? And again, preferences are properties that are desired but not necessarily required to be in a plan. So there are two high-level different types of preference languages, quantitative and qualitative. As you would expect, in quantitative languages, we actually assign a numeric value to the different plans in order to compare them. So this plan is a weight of 4 and a weight of 2, and that tells you which one you prefer. Here are some languages that do that. And for qualitative languages, we actually just have like this type of this plan with this property is preferred to this other plan with this property, but we don't actually know any sort of information about how much we prefer one to the other or something like that. And an important outcome of this is when you have quantitative languages, they're totally comparable. So for any two sets of plans, you can determine which one is preferred. Whereas in qualitative languages, you could have a situation where plan 1 is preferred to plan 2, and plan 1 is also preferred to plan 3, but that doesn't give you any information about whether plan 2 is preferred to plan 3. So it's a little bit less expressive that way. So to go into how you actually express preferences in PDDL3, like we talked about with temporally extended goals, there is some PDDL3 syntax to do this. There's a label, the preference label here, which you can put on fluents to represent things that you prefer. And then there's a function called isViolated that essentially returns the number of times that any fluent that has a preference label was not satisfied in your plan. So for example, if you had the preference traffic light is green until it turns red, so here's our PDDL3 temporally extended, in this case preference language, and we label it with the preference label here. This is just the name. And then our metric, our plan, basically tries to minimize the number of times that this preference is violated. So that's one way to actually express preferences directly in PDDL3. All right, so now I'm going to talk about LPP. LPP is a different language that is quite expressive in terms of the types of preferences you can represent. It's quantitative language, which means we're going to be expressing, we're going to have weights for each of our plans to express our preferences, and we can actually express kind of the strength of the preference. Goal A is preferred twice or 3 times as much as goal B. It's the extension of an older language named PP, and here's the paper if you want to actually check out this in detail. So the formulas are constructed hierarchically, so I'll go through quickly how we actually construct these preference formulas. So the lowest level is called a basic desired formula, or BDF, and that just expresses our temporally extended proposition. So this is just straight up LTL, basically, as we saw in the first section of the presentation. So I'm going to use kind of a cooking dinner example through these slides. So in this case, we always just using the future operator. So at some point, I might want to cook as part of my plan. Maybe I want to order takeout to eat dinner. And then I have some, eating spaghetti or eating pizza. Those are two different things, two different options that I could have in my plan. I don't have to have either of those, but those are just options that I'm going to have. So that's the lowest level. The next level is called atomic preference formulas, or APFs. And these are where we express our preferences between the BDFs that we formed on the previous slide. So in this example, I'm using a weight specifically to represent preferences with lower weights being preferred. So here we're saying that we prefer to cook over ordering takeout. So this is the BDF for cook. This is the BDF for ordering takeout. We can apply weights to those to express which one is preferred and how much is preferred over the previous plan. And then here's we prefer to eat spaghetti over eating pizza. So that's the second level. Third level is called general preference formulas, or GPFs. And these are where we can do conjunctions or disjunctions or qualification of our previous formulas. So for example, if we want to say, from the previous slide, we had two APFs. We prefer to cook and we prefer to eat spaghetti. And here we can express that we really don't care which one of these we want to satisfy. You can think of this as we basically try to satisfy the APF with the lowest weight. So if we have this OR operator here, that means that our planner is going to try and satisfy the lowest weight among all these different options here, which in this case is preferring to cook. That's its first goal. You can also use an AND operator, for example, and that's going to minimize the maximum weight across both of those options. So basically what it's going to try and do, is minimize the highest weight among these two options, so it's going to try and it's going to try and cook, and it's going to try and eat spaghetti versus doing these other options. Okay, so those are GPFs. And now moving on to aggregated preference formulas, which are the highest level. So with APFs, these define the order in which our different preferences are relaxed. You can, of course, express a lot of different preferences for your planner, but not all of them may be achievable. Especially if you're trying to achieve a large number of preferences at the same time, you may not actually be able to achieve all of those. So how do we reduce our set in the correct order, or in the preferred order, so that our plan that we end up with is indeed the most preferred plan? That's what APFs allow you to do. So basically, you can express using this preference operator. I want to satisfy both of these. At first, I want to try and satisfy both of these from the previous slide, and then if I can't, I want to relax it so I only satisfy G2. And if I can't do that, then I want to relax it so I only try and satisfy G1. So that gives the planner the order in which things are relaxed. And it's important here that if you have two situations which you can't distinguish from one another, or you don't really care, we establish some order. So at the very lowest type of level, we can just sort them alphabetically or something to just provide some sort of order for the planner. Okay, so this is just a review of what I've been talking about. So ADFs at the lowest level, which express temporally extended propositions. We can apply preferences to those using APFs. Then we can combine or join APFs using general preference formulas. And finally, we can aggregate those preference formulas to show, to kind of determine the order in which you should relax your propositions to allow yourself to find a plan. So using this kind of scheme in FPP, we're using both the LTL syntax and the rules that we talked about in the first section to express temporally extended preferences. The planner that's actually used to solve these types of problems is called P-plan, and P-plan can actually handle temporally extended preferences and the goal at the end as well. And it does basically a best first search among all your different options. It actually is one of the planners that uses the left branch of what Marlies showed. It uses progression to take LTL formulas at each point in the plan and determine whether you've satisfied those formulas or not, and if not, it will push them to the next state to determine, so that in the next state you can evaluate whether you've satisfied those formulas. And that's how it kind of prunes the search space and tries to always find the most preferred plan to meet your goal. All right, so that's our presentation. Any questions from anyone?
I have a question about the release notation.
Yeah.
You guys write P or rho and then release omega. But you say that omega has to hold until P happens, and they have in conjunction in one state.
No, so omega doesn't have to hold until P happens. Omega just has to hold at the last state of P. So essentially what it's saying is omega releases P. So once omega happens, P has to happen at that state, and then omega has release P. It's okay, now it happened, so P you can do whatever you want. You can be true, you can be false, and
so P has to hold until omega happens.
Yep, and then omega releases.
Okay. So the definition is just switched, maybe.
So this is the notation. It is a notation that you have P, R, omega, but intuitively.
It's just the definition.
This should be.
Oh, I see. Okay.
That's all I was wondering, because then I saw that I was confused. So that's all.
Okay, sorry.
Okay.
Yeah. Okay. But yeah, you're right.
Any other questions? Yeah.
Well, it seems to our multiple ways to express the same formula using the grammar. Is there any notion of canonical form or at least complicated form or something like that?
Yeah, there is. Typically, they actually might be able to run this slide. So on the to simplify the algorithms, they typically apply the kind of reductions that we showed in the slide to reduce the release and the globally and the future down to just the until and the next. That allows your algorithms to be a little bit more to handle fewer cases. And then they apply the usual rules, trying to push knots out to the left-hand side.